Thank you very much. I think this is a huge topic. I could talk hours and days about this. So therefore, what I've decided to do is I will focus on 5 topics where I think there is interesting, sophisticated computer science behind data stores. And therefore, I have 10 minutes for each topic. So all I can hope for is to give you a nice idea of a problem and then the idea of a solution, and then we move on. So the 5 topics I want to talk about are resilience and consensus, sorting, log-structured merge trees, never mind if you don't know at this stage what it is, hybrid logical clocks, and distributed ACID transactions. And I shall explain for each of these what's going on. So let's start with the first one. A modern data store is distributed. So that means you run it not only on a single computer, but on multiple machines. So why is that? First of all, you want to use the power of multiple machines. You want to be able to store more data, you want to have more query power and so on. But secondly, and that's maybe in many cases even more important, you want resilience. Yeah, computers do break, and therefore a reason to use a distributed system is, even if it would fit on one machine, is for resilience, that one machine can take over if one other fails. So therefore, the different parts of a system, the different machines, quite often need to agree on things, if only, for example, about the cluster configuration. And that sounds easy. After all, also people, when they work together, they have to agree about things. And well, what do? You talk about things and talk to each other. So therefore, this is all easy. So by the way, this is called consensus in the computer science. So that is all easy as long as you can talk. And as long as things work. You can simply exchange network messages and say this is the state of the art and blah blah, and then the different parts can agree. But network has outages, network packages get dropped, delayed, duplicated, disks fail, complete machines fail, complete racks fail, even complete data centers might be out of order. So the reality of computing is things fail. And the problem with consensus happens in the presence of failure. If you have a network split, you can't talk to each other. What then? And so therefore, consensus is really an art and a difficult computer science problem which is needed in data stores. And we have not even talked about attackers, which might send wrong messages or whatever. So, just to give you an idea about the solution, 1998, something called Paxos was proposed by Leslie Lamport, and more recently, Raft has been proposed. Paxos is actually a very difficult protocol. It's hard to get your head around and to understand why it works and how to do it, and it's hard to implement. There's a lot of variants for different situations and so on. And 2013, people have got together and have said we need to do something for consensus to solve this problem, which is easier to understand and easier to implement. Therefore, if you need consensus, what I suggest you do, you first try to understand Paxos, and actually I have done all this and made many mistakes, which I try to let you prevent. But you shouldn't implement Paxos yourself. That's not what I advise. Then, after you have banged your head against Paxos, what you should, and there's actually very nice and enjoyable papers about it, what you do then is you enjoy how simple and easy Raft is, and you then don't implement it either, because it's still hard to get right. You should use something which is battle tested, which has been tried and proven to work for years and has been used in production, and take something you trust. But even more importantly, don't try to invent your own. And I have made some of these mistakes. I didn't make the mistake to try to implement Paxos, but all the other mistakes I have made. Right, so Raft. I wanted to tell some idea about the solution, so I better try to explain to you what Raft is in one slide, which is impossible, but never mind. So the idea is that you have an odd number of machines and they want to agree on something. And what they do is democracy. Everything that happens and that is written to this Raft log is replicated to all other machines if possible. What they do is they use democracy. They are 3. So they elect a leader by absolute majority. And because it's an absolute majority of at least 2 members, there can only be 1 leader. Only the leader may append to the replicated log. So the idea is that you create a log which everybody has, a log of events. And the append to the log which the leader does only counts when it has been replicated to a majority of servers. So the leader gets an update, it puts it into its own log, and then it says, well, let's replicate this to the others, and if at least one other has answered, yes, I have it in my log as well, then we have a majority for this log entry again, and then we can move on and tell the client we have appended. There's a lot of smart logic, which I can't explain here, to ensure that there is essentially only 1 leader. Well, in the case of a network split, there might for some time be 2, but then there is smart logic to break the tie and say that only the newer leader counts in the long run. Anyway, the whole thing recovers automatically from failure. So if you kill the leader, the 2 others very soon will notice that something is wrong, and between them elect a new leader and move on. So that's the whole idea. Sounds simple. It's still a lot of fun to get right. And fortunately, we have a proof, a mathematical proof, that if you implement it correctly, then it works. That's more than you can say about many algorithms. And what does one do with this replicated log? Well, we just say the entries in the replicated log are the transactions which change a key value store, and then this whole thing can play the role of a key value store and can, for example, be the central piece of a cluster to store the cluster configuration. Right. Let me quickly show you a picture, a movie actually. So this is a Raft cluster. By the way, I didn't do this myself. This is one of the authors of the Raft paper who has implemented this. You see 5 servers, and in the beginning there's no leader, and they somehow wait for some timeout, which is random. So now this server has lost the patience and said, we need a leader, we need to do something. And what it does, it sends out messages to everybody and says, elect me. And so the messages come back, and if somebody hasn't elected in term 1 for anybody, hasn't elected anybody, then they say, okay, you can be leader. And so if the majority of votes come back, then this is now the elected leader, this one. And the others have a timeout, which is also random. And as long as the leader regularly sends heartbeats to everybody to say, I'm the leader, I'm still there, I can reach you, everything is fine. Everything is okay, and this stays the leader. Every write request has to go to the leader and is then replicated to the others. I think we can play a bit with this. I think I can send a request. So this is now appended in server number 3. It's replicated to the others. You see here the different logs of the different machines and how they advance. I can put multiple requests. And you see it's first written into the log of S3 and then is replicated to the others. And I think I can even time out this one. Or do I have to stop it? I can stop this server. Now the others lose patience. They don't get a heartbeat. And at some stage, I think this one will be first. It says, something is wrong, elect me. The others elect him, and now this is the leader. The crucial thing is there's no single point of failure. After some time where the leader is gone, and this is usually milliseconds, or 100 milliseconds, or 250, or whatever, the others recover elect a new leader, and say everything can move on. So therefore, if you have 5 replicas, then you can tolerate the loss of 2, and the others can still move on. And if you have a split brain, if you cut the network connection into pieces, then, well, only one of them can have a majority, and that half of the brain can move on, and the other is blocked. And this is basically the idea behind this raft. Oh dear. This is a catastrophe. This is not my computer. I have to find my representation again. Here we go. Now I have to find the full screen button. Control L, very good. And now I have to scroll forward. And all is fine. And I've spent about 10 minutes. Good. Right. That was the first topic. And unfortunately, I can't go into more detail. But these slides, which I will make public, have in the PDF all the links. You can study the paper. You can go to the software, you can find implementations, you can look at this little thing, and you can have fun with it. Right, next topic is sorting. I think I don't have to explain why a data store sometimes needs to sort things. You have to index things, you have usually practical applications for sorted indexes to find something quicker, to do range queries and so on. So a data store needs sorting. Unfortunately, most published algorithms, if you open the art of computer programming, most of these algorithms which are analyzed there and are known good are actually rubbish on modern hardware. Why is that? What traditionally is done, usually you compare things, and what you do for sorting, you count the number of comparisons you have to do. And you might know that it is log n times log n to sort n things, usually. It's the complexity. And then you have to move about things a bit to interchange things. And unfortunately, the problem with nowadays machines is no longer the computing power. Computers are so fast, they can compare things so incredibly fast, that the actual problem with sorting is to move the data to the CPU. Just to illustrate a bit, when I was a kid and played with the Apple IIe, this machine had 1 megahertz. These days we have computers with 2 gigahertz or whatever, or 3 gigahertz. So in one cycle at the time, I think an instruction to compare a byte with another byte took 2 cycles. So that's 500 nanoseconds. Today, a single core running at 1 gigahertz executes 4 to 6 micro instructions using 64-bit values in one cycle. So a single CPU has increased in power by about a factor of 20,000 since I was a kid. If you look at memory access, main memory access, which is supposed to be fast, well, it has increased by a factor of 40 only. Okay, you have wider memory buses and you can shuffle around more data, fine, and you have SSDs instead of floppy disks, right? That's all fine. But main memory access is 40 times faster. Now, this Apple IIe, this had a single core. Modern machines have 32 cores. If you take this together, then during my lifetime, the discrepancy in speed between memory access and computing power has changed by a factor of 1,280. And that is why, if you do a standard sorting algorithm and don't pay attention, the bottleneck for the sorting is actually the fetching of data from main memory into your CPU, not the comparisons. Therefore, all these nice intelligent analysis is essentially void because it just doesn't look at the right problem. Right, so what can we do about this? Can we sort data in memory using 32 cores at full CPU speed or not? The answer is we can. We just don't, we must not read the books and read how it's done there. You can forget about quicksort. You have to do something else. And in a few minutes, I want to try to explain what you have to do and how it works. One approach to do this is merge sort. That is essentially the idea. You take little sequences of your data which is not yet sorted, and you first sort just little sequences. If you look at a small piece of the data, then it will fit into level 2 cache, and it will be much faster. So therefore, you can sort this in the traditional way. Now you have lots of little sequences which are already sorted, and what you have to do is you have to merge them. You have to make a larger sorted list by taking the smallest of these in the beginning first, and then the second smallest, and so on. And you can take advantage of the fact that they are already pre-sorted. So far, the idea is simple, but now you have to make sure that if these pieces become larger and don't fit anymore in level 2 cache, that still most of the comparisons you do actually compare stuff which is in cache. That is the fundamental idea. And what you do is you use a minimal heap. If you know what it is, okay. If you don't know, this is just such a binary tree which is balanced with a property that whenever you look at any place, the item which is in some node is larger than both its children. Yeah? And it's relatively easy to insert into such a heap. The cost of inserting is just essentially proportional to the height of the tree. So the basic idea of this algorithm is you take these things and you want to merge them. What you do is you take the first few of these, which are the smallest in each sequence, and you insert them into a heap. Now, if you think about it, if the heap is small enough such that it fits in L2, then you fetch a point, and okay, this is the main memory fetch, but then you compare that new guy with things which are already here in level 2, such that essentially all comparisons come from level 2 cache. And that is the secret to make it so that the data you want to compare actually arrives fast enough in your CPU. And if you do that, and there's a lot of details to be sorted out, then you can actually implement a sort which uses this merge sort idea and can consume the full computing power of 32 cores on a modern machine, which essentially means it runs 32 times as fast as your standard implementation, for example, in the standard template library of C++, which is single-threaded. Here you go. You should do that, otherwise your database is a lot slower than competitors. Next topic. Good, 20 minutes. Next topic is log structured merge trees. Before I explain what it is, just roughly, let me tell you what the problem is. If somebody downloads a database, and this is now not only true for distributed, but also for single server databases, what they expect is that the database can hold more data than fits in RAM, unless the data store is sold as an only in-memory data store. That's what people expect. If they have a 64 gigabyte machine with a terabyte SSD, they expect they can store about a terabyte of data in there. They assume that it works well with modern SSDs, that it works with disks, spinning disks, and they assume that they can write to the database quickly. And furthermore, they assume that if they only hit a part of their data which actually fits in RAM, a so-called hot set, then they would hope that the access to that hot set is as fast as memory access. Because you don't want to go to your spinning Rust just to get a piece of data back in case you just got it anyway. So proper caching is what they expect. Now, traditionally, data stores have used binary trees or B+ trees or whatever, these balanced binary trees, and then with lots of tricks and so on. But these traditional things, they traditionally fail with the last two requirements. Now, if they run out of, in particular, if you do random writes, yeah, what happens is that the tree is essentially put out on disk, and the moment you have to insert something far low in the tree, then you have random disk accesses, and horrible things happen with your performance. Likewise, with RAMs, you have to do aggressive caching to get this fast. So, and this is the problem log structured merge trees attack. Again, I stole this picture from a link from the Wikipedia page, but you can find the original and a very nice article about this linked down here. So let me explain what the basic idea behind log structured merge tree is. And again, I have only 4 minutes or so I need to necessarily skip a few details. All these things which you see here are individual data files, some larger, some smaller, which have been sorted. And the basic idea is that the database tries as much as possible to keep these data files immutable and to write them in a linear fashion. Because if you write to some SSD or disk linearly, block after block, then this is fast. If you write here and here and here and here and here and here, then it is very slow. What happens if you write here and here and here and here and here, then you get so-called write amplification, and you believe you write a megabyte, and your SSD actually has to write 100 megabytes. That is because SSDs, they cannot just change a byte somewhere. If you want to change a byte somewhere, you have to erase 2 megabytes and completely write them anew. And you change just 1 byte. So what you have to do is you have to write linearly. So therefore, these files are organized into levels. And level 0 essentially resides in RAM. So if you do a bulk write, if you do lots of writes, what it does, it uses a traditional tree structure in memory to make so-called mem tables, which are sorted, but which are kept only in memory. Now, the moment you have a lot of these things in level 0, some background process goes away and says, okay, let's take the smallest few from these and merge them into one contiguous file, which is sorted, and then the larger things into the next one, and yet larger things to the next one, and also incorporate things which are already at level 1. So what it does, it fetches maybe 1 file here, 3 files here in memory, does a merge sort, maybe along the lines which I just described, gets a sorted file for level 1, and then writes it out in a single go, which is fast. And then the data structure is restructured by switching a switch, and it's again consistent. So the idea is if you look for something in this data store, what you do is you first look at level 0. You have a sorted mem table, so you can quickly find things. If you don't find it there, you go 1 level down. If you don't find it there, you go yet again 1 level down. Obviously, most of the data will be just on disk, so you have to go out to disk. But those things which have recently been written or recently been read will reside in the upper levels, and access is fast. And writes, bulk writes, can be very quickly because they are just done in memory, unless you ask for syncing them to disk. That's the basic idea. There's one thing missing, because quite often you want to save some work in case you suspect that a key you want to find is in this file, but in actual fact it isn't. So what is then also used is a nice trick called Bloom filter or cuckoo filter, which is a data structure which is small, much smaller than the data, and which you can hold in RAM, and which you can use to prove that a certain key does not occur in here. So sometimes it lies, sometimes it tells you, it might be here, and then it isn't. But most of the time it gets it right, and it will never say it's not in there, and then it's in there. So that's the thing, and so therefore you can, when you do lookups, you can sometimes quickly decide, I don't have to look in this file, I can just move on, and this saves you a lot of disk accesses for reading. So let me summarize. Log structured merge trees. The writes first go in level 0 into memory. All files which are created, except the ones in level 0, of course, are sorted and immutable. This compaction procedure moves stuff from the higher levels down to lower levels and only does merge sort in memory. We can use merge sort, which is quicker than other sorts with nowadays technology. And all writes are sequential. and we use Bloom filters or cuckoo filters to get fast reach, such that we don't have to reach out to disk if things aren't there. The net result is that we have very good write throughput, we have reasonable read performance, and much better compromise than old technologies. I think the most well-known things using this are LevelDB, which was first developed in Google, and RocksDB, which was forked from LevelDB. But nowadays, a lot of things use this technology behind the scenes. WiredTiger, which is used by modern MongoDB storage engine, first used binary trees, and nowadays you can switch between binary trees and log-structured merge trees. I think at this stage I should admit that I work for ArangoDB, which is a relatively young database, and we are just in the process of releasing a new version which has two alternative storage engines. One which is our old memory mapped files storage engine, and the other is based on RocksDB. And the reason we do this is that we had a lot of trouble with the old storage engine if things didn't fit in RAM. And so we need this technology with the log-structured merge trees to get good write performance and good read performance in case things do not fit into RAM. Right, so if you have the PDF, all these blue things down there are links to the data stores, and you can find documentation or source code for most of them. Right, again, 10 minutes later, it's time to move to the next topic. And this is hybrid logical clocks, because there's a fundamental problem in distributed systems, namely, there is no thing like absolute time. First of all, there's of course general relativity, but that's not the big problem, at least not if unless you are have very accurate atomic clocks, which Google has. But the problem is that you see clock skew. The different clocks in your different servers are just not in sync. So therefore, if you take timestamps, even if you do network time protocol, you see differences of up to 20 milliseconds or even more sometimes. And that is a problem because you just can't compare timestamps coming from different machines. Yeah? And therefore, it's a nice hobby by Kyle to mess with the clocks in systems to break databases in his Jepsen tests. Why do you need things like this? Well, in the distributed system, you want to establish when something has happened after something else. And things happen on different machines, and you want to compare that. Say there's a write to this machine and another write to this machine, and you want to decide which one was later. Well, you are out of luck. You want to have time to lives, you want to have conflict resolution, you want to sort your logs by time, and blah, 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 blah. It's a big mess. So very quickly, what is the idea? So every computer has a time, and you make sure that it's approximately in sync. Now, if two things which happen on different machines somehow are connected by causality, that means that something has triggered an event, and that led to a network communication, and then something happened on the other machine. That is what you really want, is that if such a relation of causality is, then you want that the timestamp for the cause is smaller than the timestamp of the effect. That's the big problem with clock skew. Now, causality in such a distributed system can only be happening if there's messages exchanged. So therefore, the idea of a hybrid logical clock is the following. Whenever two machines in your system exchange a message, if server A sends something to server B, it first reads its clock and sends the timestamp over. And the receiving end, the server B, looks at this message, looks at the timestamp, and says, well, if the timestamp is smaller than mine, fine. And if it's larger, then it advances its own clock. Obviously, it's not quite that easy. What it does, it takes essentially, if it then asks for the time locally, then it takes the maximum time of its own clock, which goes on, and all the incoming messages it has ever seen. So it keeps track of the largest time it has ever seen in any message, and at all times, if asked for time, it gives either this maximum or the own local time if that is larger. So that is essentially, it moves forward its clock, but as long as no messages come in, the actual time can catch up, and so therefore it can make sure that it doesn't repeat a timestamp. Things on the same machine just see ever increasing timestamps, and if two things are connected by causality, then the timestamp of the effect is larger than the timestamp of the cause. There's a good article behind this, and there's also a published paper which you can find from this page. It's very interesting indeed, and it is necessary for the last topic I want to touch. And that is at the same time the most difficult one. It is distributed ACID transactions. I'm sure most of you will probably be aware. In a database, for many, many years, in a single server relational database, the gold standard was called ACID. That is, your transactions are atomic. A transaction either happens in its entirety or not at all. You can see a consistent state. You don't see half a transaction. You only see a set of transactions being executed, and then some maybe not yet. Two different transactions can't see each other if they are running at the same time. And if you write it and the database has confirmed it, it is durable. It is stored to disk. And if in case of a crash, the data is still there. Now, this is actually very difficult to achieve when two things come together. One is that you run transactions at the same time. It's relatively easy if you say, okay, let's first do this transaction and then that and then this, then it's basically not so difficult, but it's still okay. And the other thing is distributed, because people, the different servers, have to agree on what is the state of a transaction. Now, let me mention a few problems here. Imagine you have a distributed system and you want to run multiple transactions at the same time. How do you make sure that all the nodes agree on the fact that a transaction has happened or has not yet happened, or agree on the fact that it was committed or aborted? That is somehow atomicity. How do you create across the distributed system a consistent snapshot of the data where a certain set of transactions has been executed and the other not? How do you do that? That's consistency. How do you hide activities which happen in your data store because a transaction is ongoing and maybe writes a lot of things? How do you hide this for the eyes of another transaction which is going on at the same time? So that's your isolation. And how do you handle durability? How do you handle if a machine is lost, a disk is broken, or corrupt? So you see, with all four of these things, there is a humongous amount of problems with distributed transactions. And of course, to make things worse, you have to take into account replication, you have to take into account that you want to have automatic failover and a resilient system. And this resilient system, with all failovers, in all failure cases you can handle, it should still be ACID. So therefore, it's difficult. And if you look at what data stores do, most of them don't even try to implement it. Traditional relational databases are single server, so they are not distributed. Those NoSQL databases which are distributed quite often say, it's too hard, we don't do it. Or it's maybe not too hard, but it's not efficient enough. And there's only very, very few players who actually pull it off. The most notable one is probably Spanner by Google, not open source, and CockroachDB, which is open source. And if you notice where we are, I've put us in both. That's of course a lie in a sense. Our single server is completely ACID. And if you run ArangoDB as a distributed cluster, then it is ACID for single document operations, but not ACID for multiple document and multiple collection operations. But we are trying to get there, and I really hope that later this year we will have a version with that. There was also FoundationDB, which was a I have to say was, a transactional key value store, but it has been bought by Apple and wasn't open source in the first place, and so therefore it's gone. You cannot use it anymore. I might have forgotten some, but if the overwhelming majority of distributed systems doesn't offer you multi-key ACID transactions. Right. So this is already my last slide, but we want to have some time for questions, so therefore I will only spend a few minutes on this. And again, I can only give you the rough idea how one could possibly pull something off. The first idea to understand is so-called multi-version concurrency control. And if you think about it, you have multiple transactions going on at the same time, and say you have a key value store, and one transaction modifies a key. Because of your isolation properties, you don't want that the other transactions, if they read something, see the change. So therefore, you essentially are forced to keep the new value for the new transaction and for the future, and at the same time keep the old value for the other ongoing transactions to still read. And that is what is meant here with multi-version concurrency control. You keep multiple versions of your key value pairs for a single key, multiple versions, and make sure that every transaction sees the right one, even if they are concurrently running, and for that reason must see different versions. So that's the first thing you have to do. Now, basically, if you have a distributed system, you don't want to do something like create a bottleneck somewhere in your cluster and push every single transaction through that. Yeah? So that's just not scalable, and it doesn't work fast enough. So therefore, the next thing you notice is that what you have to do is you have to make all these manipulations of your transaction in all different parts of your cluster, but they must not yet count. So therefore, what you essentially do is you do the manipulations, you add new versions of key value pairs, but you make sure that before the commit has happened, other transactions can't see it. So if the database is hit by a read during your transaction, by some other transaction, then you just give the old value. And then, of course, you need somewhere a switch. So for this particular transaction you are running right now, you somewhere in the system need a switch which says this transaction has committed, or not yet, or has aborted. And again, you cannot have a single place where you keep these switches, because if people run multiple transactions, then you have to scale out and be aware that there might be multiple such switches at the same time. So therefore, you have to somehow scale and shard your set of switches as well. So we have to move them all over the place. But for every single transaction, there's a single place in the system, and maybe some replicas, of course, which decides whether this transaction has yet committed or not. Which, of course, means that if you read some key which has been touched by this transaction, then you ask yourself, is this already visible or not? Then you have to consult the switch elsewhere to see whether this transaction has committed or not, and get this result back, and then deliver either this or the old version. And here we see time and hybrid logical clocks again play a role, because you are reading this transaction somehow with a timestamp. That's the simplification of the idea. You have a timestamp when this transaction should be reading. And so you have to compare whether the switch has been thrown before or after the point of time where the transaction is about to read. And here we go. These timestamps are taken on different machines, and we have all these problems with clock skew. And so, for example, the approach CockroachDB takes, well, let me start. The approach Spanner takes is they put atomic clocks in the data centers and see to it that the clock skew is very, very small. So therefore, they have to consider only small tolerances when they compare timestamps, and can get away with it because they are Google. Now, Cockroach must run on commodity hardware. So they have to live with a clock skew of, say, up to 100 milliseconds. And so sometimes they have to wait until time has passed such that they really can be sure that the two timestamps compare in this or that way. And they use the hybrid logical clocks to at least ensure that if there's causality between two events, the timestamps compare. Right, that's essentially what I already said. These switches, they need to be persisted for durability. They need to scale. You don't want to have a bottleneck just because of these switches. They need to be replicated because you don't want to lose your values of these switches. And they have to be resilient, so you have to solve all these problems for these switches as well. And therefore, that's a hard problem. I think in one publication of FoundationDB, they donated out of an 800 CPU cluster, I think they donated 496 machines or CPUs for transaction management for these switches. So that's something you have to keep in mind. Anyway, on top of this, you have to implement this MVCC logic. Timestamps play a crucial role. And isn't it all a lot of fun? It's really difficult. It's difficult to get right. And maybe if I give a talk next year, I hope that I can report that we have done it for ArangoDB and we have distributed transactions. This would be a major achievement, but don't hit me if we haven't managed to do that. Anyway, I've collected a few links and I'm happy to answer your questions and now and later. Thanks.
Thank you, Max. Who has a question for Max? Is that a hand? Yes, brilliant.
I have a question on the section on sorting, actually. So, when you're, can you go into a little more detail there? Because when you're sorting, there are various ways you can do it, right? You can basically say, I'm sorting the keys and the pointers, in which case, you can implement a super efficient sort. But then if you actually try to materialize the result with the keys and you fetch up everything randomly from memory, that is basically where you die again. If you try to actually kind of sort variable length records then altogether, then this is actually a very heavy thing to do with, with management of memory and fragmentation and so on. So there's also a lot of complexity there beyond just, just sorting basic numbers, which is where, which is where I would like to hear if you have some thoughts on that.
Yeah. So first of all, I was assuming for this idea that everything is in RAM. It's even more difficult if you have stuff out on disk. But let's talk about RAM. Right, the easiest case, as you say, is if you have your numbers flat in memory, and you can actually just access a single cache line to do the comparison. But if you have variable length keys, and you actually have arrays of pointers, and these pointers point elsewhere, then it's not too bad, for the following reason. Whether you access a single cache line to compare your two things, or whether you use four cache lines because you need the two pointers, and then the cache lines where the stuff is they point to, doesn't actually matter. What matters is that the two things you compare have all the cache lines which consider them in second level cache. So therefore, although it's different whether you sort flat in memory or whether you sort variable length keys somewhere, the algorithm is the same. Because with this heap trick, what you get is that if you just compare things which have recently been looked at, then regardless of what the situation is, things will be in cache. So therefore, the basic idea is good if you have flat, and is good if you have variable length keys and pointers. But you're right, there's a lot of things to be answered. In particular, in the beginning it's easy because you can easily parallelize because you have completely separate tasks. Then you merge more and more, and in the end there comes a time when you don't have enough merges to make all your CPUs busy. And there's lots of little details, and I'm happy to talk more about this, but it's still quite complicated. I was happy to transfer this one idea.
Great. Who's next? We've got time for one more question. Okay. There we go. I think Stefan has another one. Excellent.
Yeah, another question on the log structured merge trees. So let's assume you're looking up something in a level of the LSM tree quite far below. It's a big level. It exists mainly on disk. And your Bloom filters have told you, okay, there might be something in there. You actually have to look it up. How do you typically search through this large ordered file on disk? You probably don't want to do a binary search or so through it. You probably want something like a B-tree style index within the level or so to kind of find within the sorted file.
The sky's the limit. The first idea is that you have a sorted thing. You might even pull the whole file in, maybe memory map it, and do a binary search. That first works. It's probably not optimal. Yeah. Second idea would be that in the sorted files, you additionally have a hash table. Yeah. But there's endless possibilities. You can have further tree structures in these files to make things easier with fat nodes and whatever. There's a lot of things, and I don't think that all tricks have been invented which are possible. In particular, I think that even what RocksDB is great, but I think even what RocksDB does can be improved.
Do you know what they do in particular for that
To be honest, I don't know all the details, but I believe they have the file sorted and they do a binary search if it comes to that. Okay. They have one more trick. They allow the usage of prefix Bloom filters. So therefore, sometimes they can even use a Bloom filter to exclude the possibility that something is there if they do a range query. But to be honest, I don't know all the details of what they do. But it's open source, you can just have a look.
Right.
Excellent. Thank you again, Max.